Good morning to all of you. In the last two videos, we discussed the topic wave, types of wave. In the types of wave, we have mechanical waves, non-mechanical waves. Again, the mechanical waves are classified into two categories. First wave is your transverse wave. Second one is your longitudinal waves. After the studying transverse waves, longitudinal waves, in the previous video, we discussed some important terms related with the wave. That important terms may be your amplitude, wavelength, time period, frequency, wave number, angular wave number, and today's video we start a new concept. That new concept name is speed of transverse waves on a stretched string. So you can see in the in the first diagram, a student created a transverse waves and the string is having two ends, and the one end of the string is held by the student and the other end of the string is fixed to the tree. When the student creates a disturbance in a up and down direction, a wave starts, and that wave is nothing but your transverse wave, because in the transverse wave the particles are vibrating up and down. In the second video, you can easily understand the concept of wave. You can see here P, Q, R, S, T, Q dash, R dash, S dash, T dash is nothing but wave. Where the first wave starts from P, Q, R, S, T. It is your first wave. T, Q dash, R dash, S dash, T dash is your second wave. The first wave and the second wave, both these two waves having a wavelength of lambda and lambda. Here the wavelength is taken from crust to crust and trough to trough. So you can easily see in the diagram, in the upper portion of the wavelength is taken from Q to Q dash. That is nothing but your crust to crust. In the below of the wave diagram, you can see the wavelength again from S to S dash, where S is nothing but trough to trough. Here the wavelength are 2. In the above of the wave diagram, the below of the wave diagram. So speed of transverse waves on a stretched string is calculated by V is equals to root of capital T divided by nu, where capital T is the tension in the string, where tension is nothing but your force is present in the string, and nu is the mass per unit length of the string, and nu is also sometimes called as linear mass density of the string. So SI unit of nu is kg per meter. So speed of transverse waves in terms of the density of the material of the string is taken as, if R be the radius of the string and rho be the density of the material of the string, then M is equals to mass of the string per unit length. So you have to calculate mass of the string per unit length. So you can easily know the basic formula, that is formula is density is equals to mass divided by volume. If you want to calculate mass, then mass equals to density into volume. But in this case, you need a mass of the string per unit length. It becomes density of the string multiply with the volume of the string per unit length. So volume of the string is nothing but your volume of the cylindrical body, because string is in the shape of cylindrical. So it becomes pi r square into L. Here the L is taken as 1 because you are calculating the volume of the string per unit length. So L is replaced by 1 and it is multiplied with the density, that is rho. So once you multiply all these terms, you get pi r square multiplied with the rho. So velocity is equals to root of capital T divided by pi r square rho. This is the velocity of transverse wave. In the next concept, we have the speed of longitudinal waves. So for the longitudinal waves, example for the longitudinal waves is nothing but your sound waves. As you can see these two diagrams. In the first diagram, you can see a pipe. In that pipe there is air. In air, some of the portion of the air particles are come closer to each other. That portion is taken as compression. In the some part of the pipe, you can see the air particles are moving away from each other. That portion is taken as rarefaction. In the second diagram, you can easily identify where is the compression, where is the rarefaction. Where the vertical lines comes closer to each other, that portion is considered as compression. Where the vertical lines are far away from each other or vertical lines are equally spaced, that portion is taken as rarefaction. So speed of longitudinal waves can be calculated by V is equals to root of E divided by rho. So root of capital E divided by rho, where E is nothing but your modulus of elasticity of the medium and rho is the density of the medium. In the mechanical properties of solid, you have studied there are three types of modulus of elasticity. The first type of the modulus of elasticity is your Young's modulus of elasticity. So in case of solid, where E is replaced by Young's modulus of elasticity, and hence equation 1 becomes V is equals to root of Y divided by rho, where Y is your Young's modulus. In case of fluid, and fluid is something which can flow, so liquid and gases both are flow, so E is replaced by the bulk modulus. So hence your equation 1 becomes V is equals to root of K divided by rho, where K is your bulk modulus and rho is the density of the medium. So in the next topic, we have the Newton's calculated the velocity of sound in air. As you can see in this diagram, there are in the starting end you have the speaker, in the next end you have the human ear. In between this there is a sound wave, and the sound wave travels in a form of compression and rarefaction. In this diagram you can see the first portion is your compression. After that you have rarefaction, compression, rarefaction, compression, rarefaction, compression, rarefaction, compression. In the compression region, the air particles are come closer to each other. In the rarefaction, the air particles are move away from each other. So velocity of longitudinal wave in a medium is given by V is equals to root of K divided by rho, where K is your bulk modulus. So in place of K, we have to write it as stress divided by strain. So stress can be defined as force acting per unit area, and the strain can be defined as change in volume to the original volume, where minus sign indicates that there is a decrease in volume. So once you simplify all these terms, you get K is equals to minus delta P multiply with V whole divided by delta V, where delta P is your change in pressure, where delta V is nothing but your change in volume. During compression, pressure increases, volume decreases. And Newton says that when a sound travels through a gas in the form of compression and rarefaction, Newton assumed that there is a change in pressure and volume of a gas when sound waves are propagated through it, are isothermal. So whatever be the amount of heat produced during compression is lost to the surrounding, and similarly the amount of heat lost during rarefaction is gained from the surrounding so as to keep the temperature constant. Thus, sound travels in air are isothermal, that is, pressure and volume of the air change, but the temperature remains constant. And this is for the adiabatic process. Oh sorry, this is for the isothermal process. PV is equals to constant, and you can see, suppose the pressure increases from P to P plus delta P and the volume decreases from V to V minus delta V, P plus delta P, V minus delta V. This is for compression. In the compression region, pressure increases, volume decreases. As the temperature remains constant, it does not change. So therefore, isothermal processes obey, that is nothing but your Boyle's law is applicable. That is PV is equals to constant. When the P is replaced by P plus delta P, V is replaced by V minus delta V. When you multiply this equation, you get PV minus P delta V plus V delta P minus delta P multiplied with delta V, where delta P and delta V are very small as compared to the P and V, so its product is also small, so we can neglect it. So then you get PV is equals to PV minus P delta V plus V delta P. You can simplify it, then last equation number 3 you get P is equals to V delta P whole divided by delta V. This is your equation number 3. Once you compare equation 2 and 3, we get in place of P, now we have to write it as K, or in place of K, we have to write it as capital P. Hence, equation 1 can be written as V is equals to root of capital P divided by rho, which is Newton formula for the velocity of sound in air, where P is nothing but your atmosphere pressure and rho is nothing but your density of the air. Once you putting all the value, you get this value. Let us calculate the velocity of sound in air at standard temperature and pressure. Once you substitute all these values in the formula, you get 280 meter per second. And this 280 meter per second is the calculated value of velocity of sound by the Newton. But the experimental value for the velocity of sound is nearer to the 332 meter per second. It means that there is a certain error. That error is how much? This error is nearly 52 meter per second. If you want to calculate this error in terms of percentage error, it comes to nearer to the 16%. And the 16% error in a physics is very large, so you cannot neglect it. But Newton was unable to explain this error. But this error is later corrected by the Laplace. In 1816, Laplace said that Newton's assumption was wrong. According to Laplace, the change in pressure and volume of a gas when a sound waves are propagated through it are not isothermal but adiabatic according to the Laplace. This is because when a sound wave travels in a medium, then the compression and rarefaction follow each other so fast or so rapidly that there is no time for the exchange of heat with the surrounding. It means that neither the heat is transferred to the surrounding during compression and nor the heat is taken from the surrounding during rarefaction. First, the process during the propagation of sound waves in the medium is adiabatic and not isothermal as assumed by the Newton. In the single statement, if you want to say it, Newton's assumption was wrong. According to the Newton, when the sound waves travels from one point to another, isothermal conditions are obeyed. But according to Laplace, he says that when a sound wave travels from one point to another, isothermal conditions are not obeyed. Adiabatic process takes place when a sound wave travels from one medium to another in a air. So for the adiabatic process, we have PV raised to gamma equals to constant. And once you differentiate equation 1, we get, after differentiate equation 1, we get differentiate it, simplify it, in the last you get minus V delta P whole divided by delta V is equals to gamma multiply with P, where delta P and delta V is nothing but your change in pressure and change in volume. According to the equation 4, in place of K, now you have to write it as gamma multiply with P. Then equation number 1 becomes V is equals to, in place of K, now you have to write it as, or now you have to substitute the value of K replaced by root of gamma multiply with P whole divided by rho. You can observe this formula. In Laplace formula, you got V is equals to root of gamma multiply with P whole divided by rho. But in the Newton formula, gamma is not there. In air, the nitrogen and oxygen gases are present, and these two gases are diatomic, and for the diatomic, gamma value is your 1.4, and this value you can calculate in the chapter kinetic theory of gases, but here you have to just remember the value of gamma for the diatomic is 1.4. Once you substitute these all values, you get velocity of sound nearer to the 332.5 meter per second, and this value calculated by the Laplace is nearer to the experimental value. So this is very close to experimental value, hence Laplace corrected the Newton's formula. So it is also called as, hence Laplace correction is justified. Thank you for today watching this video. In the next video, we discuss the equation of a progressive wave, and we can solve some problems on the equation of a progressive wave.